Uh, okay. A couple of announcements. So I somehow accidentally screwed up the release date for the quiz, and I just released it today in the morning because someone noticed that and sent me a message on Piazza. So the quiz for the last week was just released today, and it's due on Monday. Monday, just so you, if you travel somewhere during the weekend or ski aggressively, then you don't have to work on it. But I will assign the next one hopefully tomorrow, and then it will be due maybe next Thursday or something. I also tried to assign homework today, next homework. Okay, so let's just quickly recall where we are. So we actually successfully booted into the main function, right? So it's kind of a big deal, you know, like we know how the boot protocol works. We know what we need to do to get into C. If you want to work with a different language like C++ or Rust, it's relatively easy. The C++ will be a little bit complicated because, I mean, first of all, there are tutorials online, and I did it myself a couple of times, but a while ago, so I don't really remember the details. But C++ wants to have a tiny memory allocator to throw an exception. So if you really want to have C++, and maybe now, I actually didn't follow the language recently, maybe there is a mode where you say, look, exceptions are not there. But if like worst comes to worst, you need to have like a tiny memory allocator first before booting into C++. Rust is almost like C, so really nothing is required. You just set up a stack and then you go. In fact, Rust is maybe even easier than C because like all the constructors are static, or like all the static constructors are have to be statically initialized, right? So you don't need to run any constructors. But in C, like technically you can, but you can just avoid them, right? And there is a repo. I'll show you a repo later, which boots into Rust, right? So, but okay, cool. So we did it, and we said, okay, just to recall the boot sequence, I wanted to say, like, if you have more complicated languages, like for example Java, which has a runtime, right? So Java either interprets the bytecode which you run, or you do some kind of a just-in-time compilation and you compile the code and execute it natively on the machine. In case of Java, you say, look, can I boot into Java or some other language like Haskell, which has a real managed runtime with garbage collection and stuff like that? You will most likely have to implement a tiny layer, but it's very similar to how Java starts in a process, right? So process itself kind of like provides just system calls. So you'll have to boot into this tiny shim, which like provides basic functions for the runtime, and then you can enter the runtime, and then you can boot into Java. So what I'm saying is that the fact that I'm using C for this to illustrate how you can build an operating system doesn't really restrict it to anything. So there are operating systems which boot into all possible languages for all different purposes. So it's not super hard, right? I just wanted to make sure that it's clear. Arguably, however, the future of operating systems for the next couple of, let's say, years or maybe a decade will be probably Rust. So if like it's either C or Rust, and I would vote for Rust just because it provides memory safety without garbage collection, right? Without managed runtime, and so it's almost as easy to program and reason about as C, but comes with safety. So if you think of being in this space, it makes sense to invest some time and learn Rust. But okay, just a quick recap of what we've done, right? And it's nothing, it's just a recap of a previous lecture. But why we need it is just we'll in a second, like again, take a look at this figure and make sure that we understand what happened, right? But at a high level, and we talked about it for a while, so we know what's going on. We say, look, we started in 16-bit code. We set up the segment registers. We declared the global descriptor table in assembly. Again, not a strict requirement, can be done in C. We loaded this GDT, global descriptor table, into the hardware register. We switched to protected mode with a long jump. We set up the simple stack to call C functions that allow us to run the C code which we used to load the kernel from disk. So we implemented the tiny disk driver, which uses this ID interface, loads the kernel from disk into memory. Then we said, okay, sure, we're ready to run. We jumped into the entry point of the kernel. So here's the split. This was the bootloader. And this is where the kernel started. And the kernel itself said, okay, well, I want to immediately switch into enable paging switch into mode which uses page table translation. So it says, okay, I will use this like a first boot time page table. It has only 2 entries. And for simplicity, again, not a strict requirement. You can construct a real 2-level page table, which uses 4 kilobyte pages. But here they said, okay, look, let's just use 4 megabyte pages. It's enough for us to finish booting. And we'll see, like today, we'll see how we switch to a real 4 kilobyte page. And it mapped the page table maps 2 virtual regions, just literally 2 pages from 0 to 4 megabyte, and huge gap from 2 gigabyte. This is a 2 gigabyte mark to 2 gigabyte plus 4 megabyte into this single region of physical addresses. So if this is your physical memory, this is mapped 1-to-1, and this one is mapped with a 2 gigabyte shift, right? And okay, so that's where we are at this point. We say, look, the kernel sits here at the first megabyte. We loaded it here from disk, so it shows up in both mappings, obviously, right? But with 2 different addresses, and we know why we needed it, because otherwise we would have crashed the moment we enabled the page tables, because our instruction pointer was here. But when we jump to the main function, instruction pointer points somewhere above the 2nd gigabyte, because this is where the kernel is linked and compiled the link to run it, right? So, and we found it ourselves inside the main function. So we executed the entry point, and we are ready to execute whatever code we want to run inside main, right? And just to make sure, this is the layout of the machine. So like the state of the machine is after the boot, right? So we say, look, the linear addresses are enabled. So the moment your instruction pointer, for example, points somewhere here, it goes through the linear translation. However, the base is 0. So you add 0 to whatever address you have inside the instruction pointer. You end up here. You say virtual addresses are enabled. You hit this address. Now you go through a page table. The page table is a simple, like it's here on a drawing. It has 2 entries. Obviously, you take this address. Remember how we translate, since it's you say, look, we will take the top 20 bits of address and the 12 for the offset. Those 20 bits of address will be used as an index. Hold on, scratch this, I was wrong. And you guys should have corrected me. You take the top 10 bits of address, because it's just 1-level page table, and those top 10 bits encode one of the 1024 entries in this table, right? And to be exact, this entry will be entry 512. So you land on this entry, and it maps you to address 0, which is obviously like this 2 gigabyte shift, and machine just executes instruction from here, right? Is that clear how it works? I also wanted to like emphasize the fact, I keep saying virtual memory, and in the past I've seen cases where students come back to me and ask what this physical or what this virtual memory, what it is really. So it's just, wow. As we can see here, whatever number you have here inside the instruction pointer, or if you do a move instruction and you load from like EAX register or something, it's just the number. And the hardware will force these numbers through a couple of transformations. The first one is linear, which just doesn't do anything in our case to the address. And then the page table, right, which essentially in our case shifts it, subtracting 2 gigabytes, landing here, right? So this is just, it doesn't physically exist. So the only memory which you physically have is this one, right? So this is, you pay money for it. So you buy DIMMs, you plug them on the motherboard, and they provide storage. Everything else is just remapping of how this physical memory shows up in different address spaces, right? And then the hardware just maps it back to physical, right? That's clear? Good. Okay, cool. So we got to main. What do you think should happen next? Like, okay, we're ready to build the operating system at this point. A lot of kind of prerequisites are done. We booted. We know how everything works, hopefully by now. So what's next?
Should you be listening for inputs from various devices?
Good.
Like the mouse and keyboard.
Correct. So let's agree. So you say, look, in the end, we want to implement some device drivers. Like you say, well, you definitely need keyboard, or maybe in a more complicated scenario, it will be like something like graphical user interface. That's for later. Let's concentrate on a keyboard. But that's for human to interact with the system. And I agree with you, you need those. But and remember how we access the keyboard. How do we access the keyboard from a user application? Typically. How does it show up for us in your main function of your user process?
Are they interrupts?
Well, did you ever program interrupts in your life yet? You will next week. Sorry, no, after the break. So definitely not interrupts, right? You never seen them, most likely. So, but you interacted with the keyboard at least a little in your first assignment. Standard input, right? So you read from the standard input, right? So you say you are going to read from the standard input, which is 0 in a buffer. So it's a syscall, right? And somehow the standard input is wired to a physical keyboard underneath, right? So the reason I emphasize this is that I want you to remember those details, right? Someone asks you on a job interview, like, how does user, like, or how does a program interact with a keyboard? And you say, look, like inside the program, you use a system called like a read. The operating system provides some plumbing to connect to the keyboard, and we'll cover it later. And you're right. At the bottom level of this, when you press a key, there will be an interrupt. So you will get to it, but it's later. So internally in the kernel, yes, you're right. So we will have to build those interrupts to interact with devices. But even in order to boot, before even like having the keyboard, before getting to the user to shell, right? So we need probably a disk driver to be able to load the processes, or like disk from disk. And in order to access disk, you probably need something like a file system, right? So we'll have to build a file system which manages space of the disk and virtualizes it, saying that each file has a human readable name. There will be folders, symbolic links, stuff like that. So, right. So we will build a file system. We'll build the disk driver. We'll build the keyboard driver. That's all correct. Another thing, typically when we boot, we want to see some debug messages. Okay, I'm booting, like, and so we need to some kind of a serial line / VGA. VGA is something what shows up on real screen, just less sophisticated than more complicated graphical interfaces. And serial line in a data center, like there is a serial port, and typically you connect a cable because you don't have a screen for each blade in a data center. So you connect a cable to the serial line, and then the serial line goes to a special device which like converts it into the network interface, so you can access it remotely. But the point is that those are kind of equivalent, and this not equivalent, but they are like serve the similar purpose. So typically you don't have a physical display, although sometimes worse comes to worse, you know, in a data center, you drive a cart with a display and plug it into the machine because you don't even see anything on, like the serial line doesn't work, and you have to debug before even you get to those devices. Okay, cool. So this is smart. So what else we need to build? I mean, it's up to you. We can scratch a couple of things and just build this in this class and never talk about anything else. But let's build more. What is the ultimate goal for us? In the end, we want the operating system to be usable. What does it mean at a high level?
You also need the ability to, you know,
Correct. So we want to run processes, or applications or whatever. And what do you think we need to do for this? Even to boot, as you say, we need to boot into shell, right? So which is just a process, right? But arguably, you're actually absolutely right. So there are like roughly two main things which you do when you build an operating system. You build device drivers to somehow interact with the external environment, disks, I/O, like whatever, screens. But also the second most important thing is to be able to run applications. And they obviously rely on the infrastructure, which allows them to output something. But the second most important thing is to run applications. So what do we need for that? We need a scheduler. Agree. What else? Scheduler will be like picking next application to run. Okay, hold on. That's a great question, and I thought that you immediately finish it differently, but wait, hold on. L1 cache was very early in the boot stage, initialized by Intel by BIOS, which loaded some blobs of and enabled memory. And right now we have some amount of physical memory. And in real life, BIOS will advertise us how much memory we have because they know, because they initialize everything. They tell us there is a simple data structure which you can exchange with the operating system and say, look, like I have so much memory, right? So we are not running off caches. We have physical memory. But what I expected you to say is the following. You say, look, in order to run processes, right? So remember, we kind of say we read the data section from disk into memory, right? In order to do that, you need you need to keep metadata about available physical memory, right? Because when you boot it, that's our physical memory. Let me clear everything here. So you say, look, I loaded the kernel from the first megabyte, and it ends with an end symbol. I'll explain what it means. And there is some available physical memory, right? So every time you want to create a process, you say, look, first of all, I will probably construct a new page table for the process because the process will have its own page table. And maybe my goal is to load, let's say, the text section of a process into like a first couple of pages of the address space, starting from address 0. Then I will load the data section, and then I will set up a stack for a process, right? And you say, look, but those are like ephemeral virtual addresses. If they are not backed by physical memory, like you will get an exception. So really, you need to manage this available physical memory to make sure that every time you map something in a page table, you pick an available fresh page, right? Agree with this? So you need to construct this simple memory allocator, which allows you to keep track of available physical memory. And then you say, look, every time I want to start a new process, I will construct a new page table and start loading from disk. I will read this ELF file and will load it into memory of the process, right? Okay, so and that's very clever, and this is exactly what we'll start doing. So essentially, at a high level, our goal is to end up with this diagram where the kernel is already loaded in memory. And so it will run a scheduler, run device drivers, as you said. But every time we want to start a process, we will create a new page table, which will like represent the address space of this process. And we will enforce a couple of isolation invariants. So first is that the process cannot easily access the memory of a kernel. This is not allowed because otherwise any process can overwrite any kernel data structures, and then the processes can do anything they want with the system. And they cannot access memory of each other, right? So just to make sure that we can run processes from different mistrusting parties, some of it is from the web, some of it is like we wrote, but maybe we don't trust ourselves because everything is buggy. So, and we'll use page tables for this, right? So at a high level, at the very core of this idea, when you say, look, I want to run a process, at the very core is construct a new page table, like two ideas. Construct a new page table, which will represent a new address space of a process, and then load the ELF file from disk and start running, right? It's very simple, and we already loaded ELF files from disk, right? Okay, that's nice. So, like again, that's not super hard. Essentially, And again, if I ask you to like, I send you home with a homework assignment over the spring break, we need more time. I'm joking. If I ask you a question, what is the process? How can you build it? Like, build meaning you program in C. So literally, like, what will you type? What data structures you need to implement to implement a process? How do you imagine it? Any ideas?
Well, you need a page table because each process needs its own page table. So, I mean, you talked about implementing that with like a tree, right?
Yeah. And hold on, it's not like we can change it. It's done by Intel. Intel says my CPU will read a tree. So every time you want a page table, it must be a tree, right? So cool, yeah. So you say page directory pointer, page directory. You say, look, struct proc will have a pointer to the page table, right? Agree with this? What else? Yeah, process ID can be an integer. Unique ID, not pretty clear why we need it for now, but let's like, sure, we have it, right? Why not? That's a good question. We load it. And when we were loading it, we say it was linked for us to run at some address. Let's say maybe it's not 0, maybe it's 0. It's a text section. And we literally, when we loaded it, before running it, we'll set the instruction pointer to point to the entry point. So at some point you say, look, really, I don't, and every time you will be context switching to a different process, because maybe this process ran for some time and this instruction pointer changed, right? What you really need is you read the data structure which remembers the state of the registers, because every time you context switch away, you save those registers, and every time you come back, you load them into real physical hardware registers. So, and this thing is actually it's called a context on x86. So it's a data structure which saves all the registers, right? Context. And context is a pointer to a data structure which will have instruction pointer and some other registers, let's say EAX and something else, right? And this instruction pointer will be pointing to the instruction within the process or address within the process which you're going to run when you start running this process. To clean up all the resources, right? That's kind of correct, but it's a great question. So, like, the way everything will be running, right? Each process will have its own address space, its own page table. I have two here. So one is a green one and one is a pink one, right? So two different page tables, right? And when both of them will have their text section roughly at address 0, right? So you kind of know that it's there, but it's virtual memory. What you really have to keep track of is the physical memory, which was allocated for each of those processes, right? And you're right, there are multiple ways to do it. On Linux, there are complex data structures involved which track the layout of the address space, all the shared libraries which are mapped and shared among multiple processes, everything. On x86, it's a little easier. What x86 will do, it will say, look, I will look at the page table and I will look which physical pages are mapped by the page table. And I will simply walk this tree and will deallocate all pages which are pointed by the page table. So it's a little easier, but you're right. So you have to keep track of it, but you can do it through a page table. It's not ideal, but works for x86, right? But does this idea make sense that you don't keep track of virtual memory, at least on x86? On Linux, it's different, but you keep track of physical memory, right? And then, but you're right, you have to deallocate resources of the process. And also you will have to deallocate the pages which you allocated for the page table itself, because those are resources which were used by the process. But if you have this, if you have a pointer to the page table, you can walk those data structures and deallocate everything, right? That's good. What else?
State of process.
The state. Correct. That's good. So we have some state here, kind of like it will be an enum, like running, I don't know, dead or whatever, zombie. That's correct. And that's for the scheduler to decide what to do with the process. Sometimes you have to clean up. We'll see. Yeah, that's good. What else?
Like a file.
File descriptor table, right? So it will be an array of, let's say, integers, file descriptor. Like, I don't know, some max number here, right? Okay, and that's pretty much everything, what I, at least right now. And in x86, the process data structure fits on one screen, roughly like less than 20 fields. And most of the fields, the most important fields you already named. So if anyone ever asks you about like, what is a process, just remember, I mean, first, remember what will be there in a proc data structure in x86, but even this slide will give you enough to answer and impress the interviewers. Question?
This might seem like kind of a basic question, but it seems like the file descriptors in the page table would be related in some way. So I'm kind of wondering why you need both.
They will not, because like the page table, and again, it will be like it's hard to answer right now. As we go forward, you will see implementations for both of them. Page table will start today. The file descriptor table, like if I change the color here, and I kind of like zoom in here, it's an array, right? It will be, I said array of integers, that's wrong. Integer will be an index in a file descriptor table. So user will provide, when you do read 0, right? You will index into element 0, but here will be a pointer to another data structure, struct file. And the struct file will implement like some metadata, which will explain if it's for example, a console, then immediately you will go and read something from a keyboard. If it's, for example, a pipe, it will point to a pipe. And if it's really a file, it will recursively point to another set of data structures like inodes, which will keep track of where the file is really on disk. And it will, like when you say I read address 55 from a file, it will have a page table like metadata in a file system, also a radix tree, which will lead you to this location block. Maybe you're reading address 55, but on disk it can be, it's like a physical memory, but on disk it will be like FF something, right? So it's completely different address, right? So those are semantically completely different actually. And we'll see how they work, right? They represent different address spaces. One is on disk, one is a physical memory. Conceptually, because both of them will be translating from virtual addresses, like either virtual addresses of CPU to physical addresses in memory, and it's done through a radix tree. And a file will be translating from logical addresses within a file to physical addresses on disk. We will have a similar translation data structure, which we will, in case of x86, it's a radix tree, but it can be done differently as well.
So, okay, cool. So to roughly summarize for right now, just think like file descriptors are mostly related to information on the disk, and the page directory is related to information like party.
Correct. Yeah,
Okay.
correct. Physical memory. Yeah.
Physical. Okay, cool.
In the source code, there is a member called kstack. It says is a bottom-up kernel stack where this from.
Yeah. So I don't want to spend time right now, but roughly speaking, when we will be talking about the system calls, like typically when the user process is running, it has its own user stack. But the kernel cannot trust this stack, because if you execute a system call, the user might be malicious and might reset this ESP pointer to 0, or like to some unmapped page, or to page to the address which will try to override the kernel data structure. And so when we switch into the kernel with a system call, we'll be using a different stack, kernel stack. And each process will have its own kernel stack there will be a reason for that, but that's the field. But okay, so I mean, that's what we want to build. So this kind of data structure. And as we said in the beginning, there are two core ideas, like build an address space, page table essentially, and build and load something from disk into this address space to run it, right? So like text section, data section, stuff like that. We start with a page table. So essentially, each process will have its own page table. But before even getting there, we say, look, but the kernel also needs its own page table, because what if like there are no processes in the system? It can happen early on boot, or it can happen when the user terminated all processes. It's like physically doesn't happen in x86, but theoretically can happen, right? And so we will first build a kernel, an address space for the kernel, a page table for the kernel. We said, okay, right now we have some handicapped page table. It only has two pages and doesn't even map all available physical memory. So we'll switch and really start mapping all available physical memory. And in order to implement a page table, we really need to have this kernel memory allocator. So we had a like essentially, this is the slide which captures the discussion about the process. We say, look, at a high level, each process has it's a collection of resources, largely memory, which like holds the text stack heap of a process, and some in kernel state like open file descriptors, like you said, pointer to the kernel stack, ID, stuff like that, right? And our idea in the end is to make sure that processes are isolated from each other because they don't trust each other and they can't change the kernel. So they are also isolated from the kernel. To build this vision, we say, look, each process will run this address space. This address space will be split in half, right? We'll reserve the bottom part of the address space, this green one, for the process. And so essentially, we're going to load from disk the text and data sections, like the kernel will read the ELF, load them here. Kernel will set up the stack for the process, and it will set up the initial address of the heap, and then the process can grow the heap by using the sbrk system call, right? And it can grow up to 2 gigabytes. At this point, we say, look, that's it. You cannot go further because this part of the address space is reserved for the kernel, this yellow one. And right now, if you remember, so physical memory, like we mapped the kernel itself with a 2 gigabyte shift right here. So the kernel exactly shows up here, and there will be some available physical memory, some available, we'll map all available physical memory which exists here into with a 2 gigabyte shift into this upper section of the address space, right? And really speaking, what will happen is that when the process running, it just executes here, when it invokes a syscall, kind of like, let's say, read of 0, that will, like, through a controlled entry mechanism, which we'll be using interrupts, will transition into the kernel, will start running in the kernel, performing the read system call, maybe copying some data back, because the kernel will first read the disk temporarily into a buffer here, and then it will copy it back to the address requested by the user, right? But we will be switching between those parts, but the only way to switch is through the interrupt mechanism, right? So this way, the user cannot really access the kernel part, and we'll set up the page tables in such a manner that the user cannot really access a movements like a load or store instruction into the upper half of the address space. This makes sense? Right, so that's the goal. And as I was mentioning before, we say, look, each process will have its own page table, kind of like mapping, which will map both physical pages used by the kernel, like these, for example, and physical pages used by the user, so green and yellow part. It's not a coincidence that the lowest entries here are green, because we split the address space exactly at entry 512, which is exactly splits this root of the page table in two. The yellow part starts, and then the collection of second level page tables will be mapped with user privileges or without them, right? So we'll see how it's done soon. Again, I keep mentioning that each process, each address space of a process will map the kernel part, this yellow part. And one of you might ask a question, okay, is it really necessary? So why are we really mapping this yellow part in every process of a system? So for example, if we have two processes here, let me just erase all this ink. This let's assume this is the page for this for a second, which holds this virtual range. So we will, every page table, like the pink and the green, will have this mapping, right? So which is like, okay, if you're asking a question, okay, why is it needed? Strictly speaking, it may not be necessary, but it's easier and faster. So every time you do a syscall, instead of like switching to a different page table, kernel page table, you stay on the same page table. It's just that you're switching the privilege levels, and suddenly you can access the entire address space. And running inside the kernel, you can easily, like, if user provides you a pointer to a buffer where it wants to read something from the disk, the kernel can use this pointer, make sure that it points to the user part of the address space to prevent an attack. Just use this pointer and just like essentially read the memory. So it will become clear later in the class, but that's what x86 is doing. Again, I should stop and say that not all the systems do this. Linux does it, but due to like recent or not so recent at this point meltdown and Spectre attacks, there is this technique which is called kernel KPTI, kernel page table isolation, meaning that like the kernel part of the address space is not mapped on the user page table. That's to protect against the meltdown temporarily. It introduces significant performance overhead, but until the CPU designers fix meltdown attacks in hardware, which they at this point done or did for major CPUs, this technique is there. So just again, if you ever seen KPTI, this is the idea that this part of the address space is not mapped into the user page table. Okay, so any questions? Just stop for a second. Too many details, I agree. Okay, it will become clear, but just you'll be able to come back to those diagrams to like revisit. At a high level, this is our goal. We want to be able to build those address spaces, right? So with the split in half, lower part goes for the user, upper half part goes for the kernel. Coming back to the state of the machine, just pay attention to this because like everything will evolve from this figure. Right now we have this 4 megabyte page table. That's our temporarily page table, which is called entry page table directory, used early on entry. It only has 2 entries, like this yellow and this one. The first one, this one maps address 0, virtual 0, from 0 to 4 megabytes into physical 0 to physical 0 plus 4 megabytes. And the second entry, this one, maps addresses from 2 gigabytes, which is also known to the kernel as kernel base symbol, or it's like a macro, and to the 2 gigabytes plus 4 megabytes, right? And the kernel starts in physical memory starts at the first megabyte. So here it will show up at 2 gigabytes plus 1 megabyte, and will end at what is called the end symbol. And it's symbol which is introduced by the linker to make sure that we as developers know where we can compute the size of the kernel, right? And the physical address space has the following layout. So it starts from 0, obviously. We said that below the first megabyte, the memory can be used by the BIOS. So we have to be careful and not use anything here. Although we did a little bit. We used like for this kernel stack, but we made sure that this gap is available. The x86 will boot with roughly 234 megabytes of memory. It just, again, configurable. They say it's a constant, which is called physical top, phys-top. And if you have a machine, for example, with 512 megabytes, x86 will not use this chunk, right? And there is, like, at some point, BIOS and like CPU designers and hardware manufacturers, they ran out of space in this lowest first megabyte region, and they said, okay, we need a little bit more of the IO space for the BIOS. So essentially, if you do a write here, instead of like, if you do a write in a virtual address, which maps to this physical address, instead of going to a DRAM, it actually goes to something like a disk or GPU and stuff. Like it lives at the very top of the address space, this is the Control Z doesn't work. This is the address range, but this range of addresses is also reserved by the BIOS, right? So we have to be careful and never touch it, but we shouldn't really, because we will only be using memory up to fizstop, up to here, right? That's the state of the system after boot, right? Okay, so we said, okay, our first step is to build a tiny kernel memory allocator. And let me erase everything on this slide. This kernel memory allocator should keep track of available physical memory. Like really, everything up from the end symbol to this fizstop symbol is available to us on x86. We say, look, every page, and like we can compute how many pages, like subtracting those two symbols, will be available to us, and we can use them to like allocate memory for the kernel, data structures for the process, for page tables, for everything, right? But we need to keep track of which memory, which of those pages are available and which not, right? Okay, cool. So we need to build this tiny memory allocator. At a high level, we just simply need two methods. One which allocates a page, and one which frees a page from this list or something. We have to keep the metadata about which pages are available. If I ask you a question, so imagine you have a chunk of physical memory, starting from the end symbol, ending at fizstop, and it's split into pages, right? So some number of pages. And we need to keep track of which pages are available. How can you implement it? How to build a very simple memory allocator? What data structure you will use? A what? Which table? What will be inside the table?
So it would be mapping which process has access to which page.
A little simpler. At this point, we don't even track which process has access to which page. We just track the fact that the page is available or not. So how can we do this?
So that page is what will be pages that are available into my page.
Right. You can say, look, you can maintain an array. Typically, this array is called a bitmap. And if the bit, for example, is 0, it means the page is available. When you allocate it, you flip it to 1 and say this, you mark it as allocated, right? And that's nice, but what is the disadvantage of this data structure?
You don't know how much space you need for the array.
Well, if you have the fizstop symbol, you can kind of compute statically at compile time how much time you need, and then allocate, like have it in your data section. If you say, look, I'm more sophisticated, I will query the BIOS, and maybe I say, look, I understand that I have some amount of physical memory, and so instead of allocating it statically, you say my array will be sitting right above the kernel, and initially we will just initialize it with all zeros to make sure that everything is available, right? So it's also done, but it doesn't solve the deficiency of the data structure. So like bitmap, what's wrong with bitmaps? It's more of an algorithmic question versus, like we don't touch a lot on algorithms in this class, but this is one example.
The fact that it's going to be a linear search.
Correct. So because if imagine you like running for a while and all this bitmap is like 1s, 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 0, 1s, 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 0. In order to find the next 0, it's O(n), meaning it's a linear scan. And you say, look, I can leave for like, again, it's a game of constants at this point. You say, look, if this is really a small bitmap and like fits in one register, then linear scan is one instruction. But if it's a big bitmap, then it's not ideal. And ideally, you want your allocator, this alloc, to be fast, right? So can we improve on bitmap and come up with a different data structure? Correct. So you say, look, what if I will maintain available pages as a list? And again, there are multiple ways to do it. At a high level, it's a list, but you say, look, I will add a head pointer, which will point to the first available page. And then maybe inside this page, I will have a pointer to the next available page, and so on, right? And like the pages which are not on the list, they are not available, but your allocator will never return them. And only when you say, look, when you free a page, you say, look, someone give me a page, and it's a pointer, you like, or this pointer P, you say, look, I will insert this P points here, I will update the head here, and we'll put it like this, right? So list is good. Like, why is that? Because complexity of search is 0.1. It's a very small one. So it's a very small constant. You just read this variable heap or the head of the list and then like fetch the page and update the head to point to the next pointer. So it's like really 2 pointer reads and 1 update, something like that, right? So it's a very fast data structure. It will take you less than 10 cycles to allocate a page. That's nice, right? Agree? And that's exactly what x86 is doing. They say, look, we'll maintain a list of available pages. So for the head of the list, they say there is this kmem.freelist field, which points to the first available page. And then like those pages are implemented as list, right? So essentially, when you do an allocation, you say, look, I will do an alloc. You will look up the head pointer. It was pointing here. You will return this pointer to whoever called the alloc, and you will update the head pointer to the page which was pointed by the next pointer, right? It's a very simple data structure. And really, it's like this. So it's a structure which they called run, and it has just one field, which is next, right? When you allocate another page, you fetch something from the head of the list. When you deallocate a page, you just put it back on the same on the free list, right? And it's kind of like that's like nothing super hard. You can guess that this is a reasonable implementation of the data structure, no linear scan, just 0.1 complexity, really fast as well, right? Okay, so we guessed it correctly. So this is what x86 is doing. Like specifically, if you look at they call, instead of calling the alloc function an alloc function, they add k for kernel alloc. So it says this is a really like maybe with some kind of small emissions here, which we will cover later, some kind of locking, spin locks here. But essentially a k-alloc function takes this free list, remembers in a temporary variable. If it's not null, update the free list saying that, okay, next available element points to the R next and return R. Very simple, right? You can write it, not hard. That's nice. And similar K3, that's real source code from these lines. You can take a look. One interesting question. Like, imagine we booted. Obviously, this list did not exist, right? Because when the kernel was loaded, like this data structure is empty. We don't know how much physical memory is available. So we first need to initialize this list somehow. So, and there is an additional interesting detail that the elements of the list itself, they live in those pages, meaning that when we run this code, kind of like K3, we actually access those R next is like, it's right here, right? So which means that those pages on the list, they have to be mapped because mapped in virtual memory, mapped by the page table. Because if they are not mapped, then if you try to write here, it will trigger immediately an exception. So there's kind of like a chicken and egg problem. You say, look, in order to construct a page table, I need 3 pages. In order to allocate a free page, I need a list. But in order to allocate a list, I need some memory to be mapped in order to even maintain the list. So the question is like, where does this memory can come from? At least like initially. It's a tricky question, but I just wanted to set up a stage that we can actually understand how x86 does it.
Well, one idea, and I remember doing this for the malloc assignment systems, is that you can store the pointers inside of the free pages. So,
That's what we do here. The pointers are inside the free pages. Those are free pages, and the pointers are inside. But in our class, it's like one level of complexity. The page needs to be mapped in order to write into our next, which means that you cannot just pick some random page which is not mapped by the page table, right? It has to be mapped in order to access this point.
Well, the kernel has a single page that if this is going to be kilobyte pages, there should be space for enough of those inside the kernel.
Correct. And this is exactly what's happening. So despite the fact that we will be using memory up until fistop, we cannot allocate the list in those pages because those are not mapped. But here, a little bit, up from the end symbol to the end of this page, we can write because this region is mapped, right? And as long as the kernel is small and doesn't approach the end of the 4 megabyte mark or 3 megabyte because it's mapped at 1, those pages can be on the list. And we exactly this is what exactly x86 is doing. So it uses available memory up from the end symbol till the end of this 4 megabyte pages. Then, as I said, it's chicken and egg. And remember, we want to use all the memory up to the fistop. They run a little bit on this short list. And by the time they construct a better page table, that page table which covers all of it, they don't touch anything beyond the 4 megabyte page. But then the moment they construct a good page table at the end of the boot sequence, at the end of the main function, they say, well, by the way, now we can also add those pages to the list. So it's a subtle detail, I get it. So but you will see that this list is initialized twice. Initially, they only add the pages from this tiny region from end up until 4 megabyte. It's enough pages to finish booting, but maybe not enough, maybe enough to even create the first process, but that's fine. And then at the very end of the boot, they said, look, and now we switch to a new page table. It covers all available physical memory for us. Then we add more, right? So that's what they do, this two-step process. A little funky, I agree, but okay, just bear with me. Any questions about it? Okay, let's see how they do it. At a high level, again, that's the very first function which they execute inside main is this kernel init 1, and it adds all available pages from the end symbol to the 4 megabyte. And it's physical addresses. They convert physical addresses from physical to virtual and essentially add from 2 gigabyte plus whatever and to the 2 gigabyte plus 4, right? Let's take a look at what's inside this function. So kernel init 1. So we just descend into this function. And essentially this function itself calls another function, which is free range, which passes the start and the end arguments inside. So this was initialized as end, and this one 4 megabyte essentially, but converted to virtual. And not in order to put those pages on the list, they essentially just freeing the whole range. They say, look, if we will be freeing the pages one by one, starting from this vstart address here, P is initialized to vstart, going until the vend, and they use the page roundup macro to make sure that if vstart is not aligned with the page, it will be rounded up to the next page. They add it to the free list, and that essentially, not surprisingly, just puts the pages one by one on a free list, right? So again, you say, look, well, was it really hard? Kind of intuitively not hard. It's a function, it's a loop, which just puts page by page on the free list. We know that they are free, but because we booted, we didn't use those pages. So it's good to put them on the allocator. It's kind of you enter the room is empty. You say, look, all seats are free. And I will put a TA at the door and it will be assigning you a random seat, right, during the midterm. So you will, the TA will keep track of which seats are empty. He will probably be using a bitmap as a printout, right? So fast scanning. Okay, cool. One additional interesting detail, where's this end symbol come from? It's kind of like a magic. It's like in a C program, you ask yourself a question, where in memory my program ends? Languages don't have an answer. So C doesn't allow you to answer this question, but you can do a little bit of magic. So the way it's done, you declare an external symbol, extern end. So from inside your program, you can see it as a character, why is it char? Array. So it's doesn't matter. You probably can declare it differently. Essentially, it's just a pointer. And they probably want to, okay, they declare it as an array of characters which starts at the address end. And so you can access it as individual bytes. I would probably just put a void star pointer here just to be happy, but maybe there is some type magic here as well. And this end symbol is provided by the linker. Like there is a little bit of magic. When you compile the kernel, we looked at this, let me show you. We looked at the, let me pop up what I wanted. We looked at this kernel linker script. And what you can do is you say, this is when you compile the kernel itself. You say, look, put the text section, make sure that it's compiled and linked to run at 2 GB plus 1 MB. Put the read-only data section above, put something else. But at the very end of it, please put this end symbol. And this is the plumbing which is used. So this end symbol will be inserted by the linker. The linker knows when it merges all the object files which are participating in the kernel, merge all the data, all the text, all the BSS section. It says, okay, they take so much time, so much space, sorry. And at the end, we know that this is the address and we will put this end symbol and it will be initialized correctly to point to this address. So a little bit of magic, but it's useful because then you know the size of the binary in memory. Yeah.
So the variable name has to be n.
Yeah. And it's like it matches here, right? And if you grab, like it will, yeah, you saw the source code. Okay, so this is what x86 is doing as magic here. Not super hard, but still a little bit of interesting plumbing. And at the end, we get the list of 3 pages, right? Okay, cool. That's not super hard. So now we have a allocator. So we can, every time we need a new free page, we trust this linked list to provide us a free page. That's very nice. Our next step is to construct a real page table for multiple reasons, right? So one reason is that the page table which we have right now doesn't even map all available memory which we want to use. But second, also that like x86 processes are reasonably small, right? So like cat and everything, their text section typically is less than 1 page. So wasting 4 MB on this is just too much. So we will be operating with like real 4 KB page tables. Now we have essentially, when we want to construct a page table, we say, look, we got like kalloc, this page for the root of the page table from the allocator. We go construct leaves. We also kalloc those leaves and how many we need, right? So, and since we manage available physical memory, we say, look, now it's good for us to construct those dynamic data structures. And that's exactly what x86 does in this second function, which is called kvmalloc. So what it does, it says like kernel virtual memory alloc. So it initializes the kernel page table. Let's take a look at how it can be done. So again, I will ask you a question, and I understand that it's like towards the end of the class, so it's a little hard, but if you want to construct a page table, which you will be using in a kernel, what needs to happen? What kind of logic needs? What magic needs to happen? What would be the logic of constructing this page table? Let's first brainstorm for a second. Well, what is a page table? Like page table is kind of an easy thing, right? So you say, look, at a high level, if this is my physical memory, starts from 0. We say we're going to map, we forget about the end of the physical memory. We're going to go to phystal. And our goal is to construct an address space in which it's a virtual address space, right? So this page table, we will be mapping some pages from virtual to physical. we say that this 0 will be mapped exactly at 2 gigabytes because we want to shift it with 2 gigabyte shift, right? So roughly speaking, constructing a page table is exactly k-alloc a page for the root, right? Then you say, look, I will be walking page by page in this region from 0 to fistole, and I will be mapping 0 to 2 gigabytes, 4 kilobytes to 2 gigabytes plus 4 kilobytes, right? Every time you want to map, you say, look, I will check if the pointer to the next level of the page table exists. If it doesn't exist, I will k-allocate from the allocator to get this page. And I will simply add the mapping. I will say, look, this mapping points to this page. I will move to the next page and will fill in this entry, right? Let me illustrate it a little bit. At a high level, the idea is the following. You say, look, I want to map this virtual address V, which in our case, let's say, starts at 2 gigabytes, to the physical address P, which in our case starts from 0, right? And you say, look, right now, what I will be doing, I will say, look, I will take this virtual address, I will split it into 10 and 10 bits because I want to know where the, like, this first 10 will point the entry in the page table directory, right? Before even touching the page table directory, I will use a k-alloc to allocate a page for it, right? And and again, if this second entry exists, it's fine. If not, I will allocate memory for the second level with this k-alloc function. But at a high level, what I will be doing is that, look, I will use this 10 bits of address to locate the entry in the page table directory, the next 10 bits to locate the entry in the page table itself. And what I'm writing into this entry is essentially this P, because I'm saying I will, like, literally, remember, this is how the algorithm works. It's just that the lowest 12 bits of P will be nulls. So I will, instead of writing P itself, I will round it up to the page. And those will be flags. And I call them mode here. So it can be read-only, writable, kernel accessible, user accessible. And of course, you need to put the present bit, right? Agree? So it's like, do you get this algorithm? You say, look, I first allocate the page table directory. I use the 10 bits of addresses of this V to locate an entry. If this entry already points to something, that's okay. If not, I will allocate the second level. And then I will use the 10, after I allocated it, I use these 10 bits to locate the entry, and I just write into this entry the physical address I want to map the page to, right? And this is on the quiz, on the previous quiz, right? So you solve this virtual to physical address translation. And when I say, look, what about the next mapping? Well, that's very easy too. We say just to move both of those virtual to physical by the size of the page, and you literally will end up on the next entry here, and we'll write this physical address here. So it will be P plus 4K plus some flags to reflect the mapping. Yeah. No, what we're doing is just the first page table, and it's a little bit confusing, I agree, was used just to boot. And it's the simplest data structure, which allows us to essentially remember we started executing at the lower addresses, but we want to jump to the upper addresses and leave the kernel there. And it's a temporary page table, which we use for boot. But this page table doesn't even map this physical memory, which we want to use up to fistop. And again, the drawing is not up to scale. It's quite a large region, right? And what we're doing, we're saying we have two options, either, and to some degree, both options actually are fine. You say, I can either extend this page table to map everything up until the fistop and just stay with this page table, right? And that's fine. the reason for that is that you want to use all the memory available to FISTOP. You want to be able to like put it on the memory allocator. You want to write into the list. So you need these elements to be mapped. And that would be a viable strategy. So it's doable. x86 takes a slightly different strategy. They say, instead of like continuing using this page table, we're gonna switch to a different page table, which will use 4 kilobyte pages. And there is, for this page table, there is no good reason to use 4 kilobyte pages. But for processes, every time we will start creating a process, each process will have its own new page table, right? And they kind of reuse the source code. They say, we're going to use the same source code, the same code to construct the kernel page table and construct page tables for the user. But technically speaking, you can separate them and stay on this page table. But what I'm trying to illustrate right now is the source code which constructs a page table which will be used by the kernel later on, which maps all the regions which we want. By the way, we also want to use this IO space because maybe some device drivers will be using it. So we want to map it as well. But again, it's all possible with the 4 megabyte page table, but they just make this choice. But later on, the same code will be used to quickly construct page tables for the processes, and we'll just see it again. So it makes sense. Why they made this choice, it's hard to argue at this point. So I would probably, if you're a real kernel designer, you say, look, guys, I'm so cool. We'll be using hybrid page tables. So it will be a page table which combines 4 megabyte and 4 kilobyte pages, just set the flags correctly, and everything is running. They don't do it. Linux does it, obviously.
So, mapping
Correct. Almost. Like it will use occasionally because every time you allocate a page for a page table, you're kind of using it, right? And x86 doesn't use a lot of dynamic memory allocation, but we'll see how occasionally it's used. But majority of this memory will be used. Majority of this memory will be used for constructing page tables, and then for using it as user memory for processes.
So the page table that's the kernel table, this, just to clarify, is the table that we use to get the pages for all the other pages.
Can you rephrase the question one more time, and I will try to answer it. Can you say it again? Correct, the later. Like, so essentially, we get the pages, like, yeah, in order to have a new page table, you need fresh pages to contain the page table. And those pages for the page table will be taken from the free list of the kernel memory allocator. Helps? Kind of, but it will, no, I get it. It's, when you see it for the first time, I get it. The hair goes up. I will reiterate it over and over. Eventually it will become better or more clear, but yeah, you will still have to read the source code and kind of map all those figures in your head to make sure that you fully understand what's going on.
But each table doesn't fully map every 4 kilobyte page in the whole physical memory, because otherwise the page table will take up like most of physical memory.
Actually, it does. Let me explain. And again, multiple choices are possible. Let me no, first of all, the page table implements the virtual address space, meaning it's a data structure which allows the hardware to decide which ranges of these addresses are mapped and which are not. Imagine for a second that we're using, instead of using this page table, we're using some new one which we built. And imagine the page table, this new one, like maps the pages which cover the region from 0 to 4 megabytes, just for illustrative purposes, and for region from 2 gigabytes to 2 gigabytes plus 4 megabytes, right? Those pages. If you try to do an instruction which uses some address and it points here, the hardware walks this page table, like this level, says, okay, wow, this is not present, and it immediately triggers a page fault, an exception. But if you issue addresses which follow into those two ranges, everything is fine, right? Okay, you say that's lovely. The question is, you're asking how many physical pages you actually wasted to construct this address space. You can carefully count. So you obviously wasted something for the root. And actually, I claim that you wasted like 1 page for this one and 1 page for this one. So total is 3 if we just, for this concrete address space. Of course, you say, look, what if this one is growing and I want map more? Every time you add a 4 megabyte region here, you waste 1 additional page, right? So, and if you say, look, and I keep asking this question maybe in homeworks or exams, you essentially ask you, what is the size of like how many pages you waste to construct a process? And you have to compute how many 4 megabyte regions you need to map from here to here, stuff like that, right? And then you can run this equation and you have the answer, right? In the end, it's not a huge number, so it's acceptable, but it's a little wasteful. So you can, if you're really, really careful, you can say, look, I see some optimization opportunities. You can do this, right? Does this answer the question? More or less, but any follow-ups? It's better to talk about it now than later.
Yeah. So it seems like you can save a lot of memory.
Yeah, we don't. For any memory which is not mapped, we don't allocate the second level.
Oh.
And at the very first level, hardware will trigger a page fault because the bit here will not be 1. The present bit will not be set to 1, and the hardware immediately says it's a page fault. Kind of. And at a high level, the answer is yes, but it's just a little bit more nuanced. So, and I don't want to go into those nuances, but yes, at a high level, the rule of thumb is that you only map what you want. And at this point, the question, what is it you want? And x86 does a couple of weird design choices, which are debatable, but if you go with those choices, they do what they want. Like we'll come back to it. Okay. Any other questions? That's a good question. So, and again, mature operating systems make different design choices. Like on Linux, there is this process which is called out-of-memory killer, and it tries to identify the victim. Again, it's a debatable design choice because maybe the victim is a mission critical thing. Maybe it just drives the car and cannot be killed. x86, I think, will just simply panic. So it just doesn't have any logic for supporting this case. They say, like, if you run out of pages, well, good luck, you're done. But and just because for educational purposes, it's good enough. On real operating systems, it's a hard question. Like choosing a victim to kill, to terminate is a challenging design choice. And it's like, I don't think there is a clean theory for what to do, but ad hoc solutions will always be there. Any other questions? But yeah, in x86, I keep asking, I used to have this on the exam. Imagine you have a process which does a fork. It was so lovely in a for loop or something like that. And I ask how many times this fork execute, and people have to count at what point you will run out of memory. Don't worry, maybe I will not ask it this time, but it was asked in the past. And the beauty of this question is that you're allowed to use your computers on the exam. So if you're not sure in your answer, you can quickly code it up, run it on x86 and count the number of times and give me the answer. But I usually ask for some kind of an explanation, but people who do that, they can explain usually as well. But it's a good, I mean, the reason to talk about it is that really, imagine you building like a car or an airplane, something mission critical, and really you have to give an answer. Someone asks you, okay, can it crash? And if you did it in some naive way, you don't have the answer. On Linux, there is no answer. You really, like Linux is so messy that you cannot answer the question, that you cannot make a statement that it will not crash under certain conditions. So like some operating systems which are designed more carefully, they can provide a guarantee, like if it's an insulin pump, it will never crash, for example. It's a big deal in many cases, right? Okay, any other questions? We have 2 more minutes. Good, then it's a snow day. I will stop here and we'll come back and see, like, essentially this thing which I was illustrating here. It's exactly what x86 is doing. And so we'll like come back and take a look at the source code. It's not very hard, but there's a couple of details which are worth discussing to understand the address spaces. Okay, then I will see you next week on Tuesday. Yeah, see you.